All right. So ionic bonding happens when there's a metal and a nonmetal. So that means we have an element on this side of the periodic table because those are metals. And then we have an element from this side of the periodic table because that's nonmetals. And so when metals and nonmetals get together, they transfer electrons. And that's what happens in ionic bonds, transfer of electrons. So what happens is that the nonmetals are so electronegative or has so much electron affinity, those are interchangeable concepts right there, that they can actually, when they get close to an atom that has lower electronegativity or lower electron affinity, they can actually put electrons so close to them that they actually take it away the other atom, therefore making ions, and then the ions are stuck together because what happens is the metals form positive ions and the nonmetals, so positive ions, and the nonmetals form negative ions because the nonmetals take the electron away from the metal. So they form a negative ion by gaining more electrons, and since electrons are negatively charged, they become more negatively charged. So once the nonmetal takes the electron away from the metal, they become opposite charged, and then they stick together because opposites attract. So that's ionic bonding. So we have to understand the charges that several groups make. Like how many electrons will they lose, what they are called after they lose electrons or gain electrons. So what we have to know is how many valence electrons, because in bonding, it's all about valence electrons. So valence electrons are the electrons, and these little semicircles here are mean to be energy levels. So there's 2 electrons in that energy level, and there's on this energy level, and this is lithium. It has 3 electrons. Well, the only electrons that do anything is the ones that are valent, so the ones on the outer shell. So in lithium, this is the only electron that will be capable of bonding. Okay, and we go down the group. Sodium has 3 energy levels. It's got 2 electrons in that one. It's got 8 electrons in that one, and it's got 1 electron in there. And this is the only one that does the bonding. It's always the valence electrons, and so that's why they're the most important thing. If it weren't for the electrons, there would only be 118 things in the universe. But there are billions and billions of things in the universe because of that particle right there, because it allows elements to bond together. So I call it the workhorse of the atom. So what happens in a metal, and both of these things are metal, right? Both of these elements are metals. What happens, and the reason for bonding is the atom wants to get as stable as possible. That stability means that it has a full energy level. And in metals, what happens is their valence electrons are so small, right? And I did group 1 here. I took elements from group 1. So lithium and sodium are right here in the periodic table. So in group 1, there's 1 valence electron. And in each group, we can tell the valence electrons by the group number. So in group 2, there'll be 2 valence electrons. So in magnesium, it has 3 energy levels, and there's 2 valence electrons in that last one, in that outer one. Okay, so if we go across the periodic table, we know how many valence electrons it has by the group number. Now, these groups in here don't really count. They are metals, they do form bonds, but they, unlike these taller columns, they form multiple ions. So we can't say exactly what their ionic charge is going to be, their oxidation number. So, but we can these tall columns, so let's just go with that. Now this is 4. This fourth column doesn't really form ions. It's kind of in this middle place where it's got 4, and it does some weird stuff. So we're going to ignore that for right now. Those have 5 valence electrons, 6 valence electrons, 7 valence electrons, and 8 valence electrons. So if we just number the columns without numbering these ones that are short, we can know how many valence electrons we have. And knowing how many valence electrons we have means we can know what charge the ion is that it's going to make. All right. So what happens with metals is metals have a small number of valence electrons. So lithium here only has one valence electron. Sodium has 1 valence electron because they're all in this group right here, the alkaline metals. Magnesium has 2 valence electrons because it's in the alkaline metals. So what happens is, to have a full energy level, that means 8 electrons in your outer energy level. So what happens with metals is they get rid of an electron. They lose an electron because now their lower energy level is full. So they lose that outer one to go down an energy level and to have a full energy level that way. Because electronegativity, because the attraction between the nucleus and the electrons are smaller than the charges between the nucleus and the electrons of this other side, the nonmetals, is so much smaller, it's easier. I always say it's easier for them to lose electrons than gain electrons. So this lithium and sodium, what's easier? To gain 7 or lose 1, right? They can gain 7 in this outer electron shell, or they can just lose this 1, and that's easier for them because of the attraction of the nucleus isn't as much as the attraction of the nucleus of the nonmetals, so they lose the 1 and they go down an electron shell, which is full. And that's the point, is to have a full electron energy level. So so if we look at the alkali metals here, we had magnesium here, just making that 2, 3. It's got 2 electrons in that energy level. It's got 8 electrons in that energy level. It's got 2 electrons in that energy level. The valence electrons are 2. And so it gets rid of these 2 because it would either have to gain 6 or lose 2. So it's easier to lose 2. So, and that's what happens over here also. They lose 3 instead of gaining 5. So when a metal forms an ion, we do not change its name. So metals become ions. We just take the element name. So let's say it's sodium. So we say it becomes a sodium ion. So that would be Na+1. Okay. It's important to know what we change their name to, because then that helps us later when we do naming. Okay. And magnesium becomes a 2+ because it loses that 2 over there. And so it becomes a 2+ ion. It loses the 2 electrons. And so then we have the magnesium ion, which I just misspelled. Magnesium.
This takes us back a little bit.
Ion.
Fractions.
All right. So that's what the metals do. Let's look at what the non-metals do. So 5, 6, 7, 8. This is how many valence electrons they have, right? So if we have a metal, or a non-metal, we have nitrogen here. It has 2 energy levels. The first energy level has 2. Second energy level,
And it says to give our answers.
it's on row 2, so that means the second energy level. We just count over. So 1, 2, 3, 4, 5. So it has 5. So it has 5 electrons in that outer energy level. So it has 5 valence electrons. So it wants 8 to have a full energy level. So what's it going to do? Is it going to lose 5 or gain 3? Well, it's easier to gain. And it's easier to gain because the effective nuclear charge is higher, which means the attraction between the nucleus and the electrons are higher. So it's easier for this one to gain. So it's going to gain 3 electrons, right? 8, so it's going to gain 3, and its charge is going to be 3 minus. Now, when a non-metal forms an ion, and it's going to get the electrons from the metal, what we do is we change its name completely. We call it a nitride. We take off some of the end of their name and add "ide." So nitride.
60 divided by 3 is 20.
Nitride ion. Whoops.
Plus 20.
There we go. Lost it. There we go. So nitride.
So that's how we get rid.
So when we have ionic bonding, we have a metal that's lost electrons. We have a non-metal that's gained electrons. And so we always have a metal, and the metal always goes first. I don't know why. It's just the way it is. Just go with it. So the metal comes first. So let's say we have sodium.
Well, this will simplify.
And let's say we have
So we can divide by 2. So if we divide it by
fluorine.
2, top and bottom, that's the same.
So fluorine has 7 valence electrons.
10, 9, X equals.
Let's go over here. Fluorine has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. And this is the Lewis structure. The Lewis structure is all the valence electrons, because they're the only ones to do the bonding. So it's the only ones that really count instead of drawing all those rings. And then sodium has 1 valence electron. So sodium's the metal. It gives the valence electron. Well, it doesn't give it. Actually, fluorine takes it from sodium and adds it to this. So fluorine will now have 8 and have a charge of 1 minus. And sodium will have gone down an energy level, so it has a full energy level, and now will be a 1 plus. And now, because of their charges, they will now attract each other. And they will bond and become a whole new element, or compound. Not element, compound. Okay, so let's look at something that's not a 1-to-1 ratio. So that's a 1-to-1 ratio in a F 1-to-1 ratio because sodium gave away 1, fluorine took 1, and so that's a 1-to-1 ratio. So we only need 1 atom of sodium and 1 atom of fluorine, and so we would call that compound sodium fluoride. This helps you with nomenclature. All right, sodium fluoride. So we just take the names of the ions and make them the name. Okay, so let's do a Lewis structure of something that's not a 1-to-1 ratio. Let's do magnesium oxide. So we take magnesium, we take oxygen. Magnesium has 2 valence electrons. Oxygen has 5 valence electrons. I'm sorry, 6. Pardon me, 6. Okay. Oh, I did it. I was thinking oxygen had 5, and so I did another 1-to-1. So let's just see what happens. So oxygen attracts these 2 electrons. And so magnesium, let's go with those 2. Oxygen takes those 2. So we have another 1-to-1. I'm sorry. I didn't mean to do another 1-to-1. And so we have magnesium. What's this called? Magnesium oxide. Now, let's do what I meant to do just now, which I didn't do. And let's do that. Let's do magnesium and nitrogen. This will do what I want it to do. All right, magnesium, again, has 2 valence electrons. That's why there's only 2 dots around that Lewis structure. Nitrogen, let's do that different color. Nitrogen has 5 valence electrons. Okay, it needs 8, so it wants to gain 3, right? But magnesium can only give up 2. It's not going to give up anymore. So these 2 go over here to nitrogen, and nitrogen's got 7. It's like, hey, I need some more, please. So these things never exist by themselves. There's always more around. So what nitrogen does is it takes 2 more from magnesium. It brings another magnesium and takes 1 from another magnesium. So now this nitrogen has 8, but this magnesium still's got 1 to get rid of. So it finds another nitrogen. So we have nitrogen, which has 5. Oops, 5. And it needs 3 more, and this magnesium can only give it 1. What do? We add another magnesium. With 2 more, it goes there and there. And so now, oops, now we have the correct ratio between these 2 elements. So these elements will bond in this ratio because we need this many to assure that every atom in the compound has a full energy level. So for this compound between magnesium and nitrogen, we're going to need 2 nitrogen atoms, and we're going to need 3 magnesium atoms to assure that every atom gets a full octet. Now, do we want to have to do this every time? No, we don't. So there's an easier way to do this. And I know you wish I would have showed you the first time, but you need to know why we did this. So what you can do is this. Let me get it bigger. That's not bigger. That's not bigger either, but whatever. All right, so magnesium forms a 2+ ion because it gets rid of 2 electrons. And then nitrogen forms a 3- ion because it pulls in 3 electrons. So what can happen is you take the charge from the magnesium and put it down here. Take the charge from, charge from nitrogen, put the 3 down here, leave the minus. Take the 2 from the magnesium and put it down there. So you can see that by what we call this is crisscrossing the charges, we can come up with this formula and not have to do all this Lewis structure stuff. So once we cross the charges, the 3 goes here, the 2 goes there, and we come up with the same ratio we did when we just did the Lewis structure. So that's the easier way to do ionic bonding. And what this would be named is magnesium nitride. Okay, all right. That is ionic bonding.